Hey there, we're going to work number 2 from your Connected Objects 2 assignment. And for this problem, it says we have two blocks that have a mass m, and they're connected by a string T2, and they're pulled to the right by a string T1, and they're also pulled to the left by another string T3 that is less than T1, and it gives us a coefficient of kinetic friction for the blocks, and it is mu k. So we're going to start out and draw free body diagrams for the two objects here. So for block 1, we have FG that's going down. We'll put FG1 there. We have the normal force that's going up. We have T2 to the right. We have the string T3 to the left, and it should be shorter than that one there. And then we also have friction to the left. So we'll put some friction there. For block 2, we have the FG going down. It should be the same size as FG1. And then we have normal force going up. We have string T1 to the right. This one should be larger than the other T2 and T3. We have T2 to the left. It should be the same size as the T2 on the other block. And then we also have friction to the left. So we have the free body diagrams, and now in part C, we're asked to derive an expression for the acceleration of the system. So let's go ahead and make our system of equations here. For block 1, the net force is going to equal to T2 minus T3 minus kinetic friction. And for the net force on block 2, it's going to be T1 minus T2 minus kinetic friction. So we're going to add those up to get the net force of my system. And if I look at that, my T2s will cancel out, so that's my internal force there for the system. And what I'm left with is T1 minus T3 minus friction minus friction. And from here, we can go ahead and start doing some substitutions. So we have the net force on the system is going to equal T1 minus T3 minus, and for kinetic friction, remember kinetic friction is equal to mu k times the normal force. So I'll put mu k, and in this case, my normal force is just equal to the weight, which is mg. So it's going to be mu k mg minus mu k mg. Okay, there's two of them, so now we can combine those. So the net force on my system is going to equal T1 minus T3 minus 2 mu k mg. And now we can go ahead and solve for the acceleration of my system using Newton's second law. Okay, the acceleration of the system is going to be the net force on the system divided by the mass of my system. And we've solved for the net force. That was equal to T1 minus T3 minus 2 mu k mg. And we'll put that all over the mass of my system, which is m plus m, or 2m. And now we've solved for the acceleration on this system. In part D, we're asked to derive an expression for the tension string in string 2. So it doesn't matter which one we kind of pick here. I'm going to pick the first one just because in the first one, that T2 is already positive. So let's write that one out. Net force on object 1 was equal to T2 minus T3 minus your kinetic friction. We're solving for T2, so I'm going to add T3 and add friction over to the left side. So we have T2 is equal to the net force on block 1 plus T3 plus friction. Now we can substitute for friction and the net force. So T2 is going to equal, we'll apply Newton's second law here, so M1A1 plus T3 plus, for friction, we got mu k times the normal force, which is equal to mg. And the last substitution we're going to do is we're going to plug in your acceleration, okay, with the acceleration that we just derived. In doing that, we would have T2 is equal to mass times T1 minus T3 minus 2 mu k mg. That's all over 2m plus T3 plus mu k mg. And if you left the answer here, then that's fine. You can just leave the answer here. If you wanted to, you could go in and simplify a little bit more and cancel out this m with one of those m's. But you could just leave the answer here with the one that we had on there. So it's the same process we've been doing. Okay, you find your or draw your free body diagrams for the two objects here, make your system of equations and solve for your net force of the system. Then we solve for the acceleration of the system. And then from there, we can solve for that internal force.